Hi class, it's Mr. V, and this is Illustrative Mathematics. We're in geometry, solid geometry, chapter 5 or unit 5, and lesson 6, which is scaling solids. And the idea for you today, the objective is that you can say, I know that when a solid is dilated by a scale factor of k, its surface area is multiplied by k squared, and its volume is multiplied by k cubed. That's where we're going today. I will show you a picture of this later on so that you can see what we're doing with it, how we're looking at this. So each of the following 4 problems are supposed to be done mentally, and then I want you to explain to me your strategy of how you did them. So please pause the video and try to do pages 5, 6, 7, and 8 and do them mentally. And then I'm going to show you some strategies that some students have used to do this. We're looking for the volume. Volume of a cube is the length times the width times the height. Sometimes we just say it's the side length cubed, and it should be edge, but they call it side. So the volume is equal to length times width times height, or sometimes they just say it's the side length, whatever the side length is, cubed. And this is actually called an edge in 3 dimensions, but they use S to determine it. So this would be 2 times 2 times 2. And we all know that 2 times 2 times 2 is equal to 8. So did it mentally. I did 2 times 2 times 2, and I said it's 8. This is meters times meters times meters. So my units are meters cubed. And that's the volume. On the next one, 5 times 5 times 5. Maybe, well, what some students did was they said, they said they have 5 times 5, and then if you multiply 5 times 5 times 5, so if you have 5 quarters, basically, is what they're asking. How much is 5 quarters? It's $1.25. And this again is units cubed, so it's feet cubed. And I'll put the units in brackets. I'd like to see that, and circle my answer. Here we have 1 times 1 times 1. 1 times 1 times 1 is 1. And my units, again, I've got a length, a width, and a height component. So this would be centimeters cubed. And the last one is a little bit more tricky. How would you multiply 1/2 times 1/2 times 1/2 in your head? What would you do to do that? And I don't know if you think of this visually or some other way. And actually, this is this slide on here. Maybe you think of it by a ruler. If you have a tape and this is 1, let me see if I can close this thing down a bit. If this is a length of 1, half of that is right here. So there's 1/2. And if you take half of a half, that's half times a half, that'd be 1/4. And half of a half is 1/8. Is that the way you did it? Another way of doing this is to picture how many cubes could you fit into a large cube. So for example, if I had a large cube here, and I could divide it up, and I divide it up, half of it is for the bottom, half of it, and then I take it half this way. Can you see one of these, when I divide it by half, it's going to be 1/8. Maybe you did this in 2 dimensions, and you said, if I have a large rectangle, and I cut it in half this way, this is 1/2. I take half of that to get half of a half, and half of a half of a half. And of course, if you divided each one of these, there'd be 8 pieces total, and we're looking at one of those slices of 8. Anyway, half times a half times a half is 1/8. And now we come to this applet here, and I've already filled in a lot of this, so I'm just going to show you my screen here. Let's see, can I do this? Let me just erase this so you can see this. I don't want you to see all my answers here. There's an applet on this page that you're supposed to open. And let me just copy this over to my whiteboard so you can see it. And we're going to look at the scale factor of this 1 by 1 by 1 cube. So, and we're going to find out what is the surface area of a new cube. and what is the volume? And this is the bulk of our time today is going to be spent doing this little activity. So if I open the applet, it looks like this. And I can have a 1 by 1 by 1 cube. And when I do this, its volume is 1 times 1 times 1. So it's 1. And so when my scale factor is 1, this 1 by 1 by 1 cube has a volume of 1. 1, 1, 1, 1, 1, 1, 1. The surface area, though, each face is 1 times 1, and there's 6 of them. So it's going to be 6 times 1, which is 6. What if we doubled this? If we were in the classroom, I'd have you build one of these out of credit cards. And then I often ask the kids, I say, well, if I were to double the edge lengths to make a larger cube, how many cubes larger is it? And they would say 2. And I say, you mean like this? I'm serious, this happens every time. It's like predictable. And they say, no, it's 4. It's 4. Oh, you mean like this? Oh, it's 8 times larger. Why? Well, you have times 2 here in the length, times 2 in the width, and times 2 in the height. So this volume, when you double the edge lengths, is going to be 8. And that goes in the thing here. Now, you should try to fill this table in on your own. I'll do it right now for you, but I just want to show you. The surface area, each one of these faces, like this top one, has a surface area of, let's see, 2 times 2. That's 4. 1, 2, 3, 4. And there's 6 faces. So it's 6 times 4, which is 24. If you do 3 times 3 by 3 by 3, then you have 3 times 3 times 3 is 9 times 20 times 3, which is 27. And each face has 9 units on it. And the 9 units, there's 6 of them, 6 faces. 9 times 6. 10 times 6 is 60. 9 times 6 is 54. Okay. What about if there's 4? 4 times 4 times 4. Can you see that that's going to be, let's see, 4 times 4 is 16 times 4 is 64. And if you do, each face has 4 times 4, that's 16. And 16 times 6, well, I'm going to use my calculator just to make sure. 16 times 6, because you can use your calculator, it's 96. My surface area here is 96. Holy shamoly. Anyway, you're going to do this. You get your values in here. 216, 6 times 6 times 6. 6 times 6 times 6. Anyway, what you're going to notice is that the scale factor is K. My surface area is whatever the surface area is. So it's going to be 6 for, there's 6 faces, and it's times K squared. And this is going to be times K cubed. My question is, well, what does this 6 stand for? Why is it going to be there? And how is surface area different from what we talked about with area, like a two-dimensional thing, just area? Well, this is a cube, and there are 6 faces. So this number is my original cube's surface area. So if I have a cube 1 by 1 by 1, this is the original cube surface area. When I scale it up, it's still multiplied by K squared, but the original one was 6. And this doesn't have a number next to it because 1 times 1 times 1 is 1. My original volume is 1. If I had a different volume for the original and I scaled it up, I would multiply it times that original volume. But the big idea for today's lesson, if I can go to my whiteboard here, is this. When we scale up a length, we scale it by a scale factor of K. This is a subscript, so L sub 2 is equal to K times L sub 1. It's proportional to the scale factor. When we do the area, it's going to be, this is area sub 2, subscript 2, is equal to K superscript, or K to the power of 2, K squared, times the area of 1. It's proportional to the area squared, and this is proportional to the volume cubed. The volume is proportional to the scale factor cubed. That's the big idea for today's lesson. Now going back to the lesson, there are some other parts to this. If you can answer these questions on page 11 and 12. On page 13 is the synthesis of this, and she asked the question, what does a 6 represent? Well, there were 6 faces on the cube, and so when you do surface area, you have to have a starting surface area. And unless it's 1, you're going to have that number next to it. And I suppose that could work in volume too, but for volume, our volume was 1 originally, so we didn't have to worry about it. Now here's one more question for us to look at. Claire says, we know that if we dilate a cube by factor of k, the volume is going to be k cubed times that volume. And it seems that this has to be true for all solids, but I'm not sure how to prove it. And then Elna says, well, earlier we showed when we did surface area, we could make a bunch of rectangles, and we could scale each of those rectangles to make any kind of shape of any solid. And you could do this with cubes as well. You could put little cubes inside of a volume, and you can scale each one of them up so that the entire solid scales up. And in fact, there's a guy who did this. I forgot his name. He does Lego models, and he gets like $30,000 for these statues and stuff. He has a museum that of Legos that he's created that go to different museums, and it's really worth it to see it sometime if you do. He quit his job as a lawyer in New York, and to glue Legos together, like to go back. And he has this special glue mixture. I've seen him work, and I've watched him work and do this. And it's cool. You take a little tiny statue, and you can make a great big one by just making bigger cubes and bigger, more Legos and fitting them all in. And so, yes, it's true that you could do that. So let's go to this question here. Suppose a triangle. I'm just put it on my whiteboard here. Suppose a triangular prism has a surface area of 84. And a square centimeters, and a volume of 36 cubic centimeters. The prism is dilated by a scale factor of k is equal to 4. And what is the surface area? What is the volume? Well, we know that if we have an area, and this works for surface area as well, so if I know the surface area, it's going to be proportional to my k squared, to my SO2. So I can substitute the values. 84, and I have 4 squared. And this will give me a number. This is going to be in units of centimeters squared. When we do volume, the volume is proportional to k cubed. So if I have a starting volume, I can multiply it by k cubed, and I get 4 cubed times the volume, which is 36. And this is equal to a number. This would have units of centimeters cubed. Now, I'm not going to multiply it out. You can multiply it out, but I'm just showing you how you would set it up. This works. And this is pretty cool. The last question for the cool down is, consider a cube that measures 1 by 1 on each side. You can think of it as a dilation of a cubic inch by for a cubic foot. It's going to be a dilation by a factor of 12. I wonder if I could do that with my I don't think it goes up to 12. It might go up to 10. And see, it goes up to 10. It's going to be this huge, huge cube. If you dilate it by 12, you would get this big block. And it's going to be a 12 by 12 by 12. So the question is, what is the volume in cubic inches of a cubic foot? Again, you take your original, multiply it by the k factor cubed to get to the one that you're going to. We're going cubic inches. We started off with 1 cubic inch, and we're multiplying each side, the length, width, and height by 12 to get this volume. And this is going to be in inches cubed. And that's all I've got for you for today. Good luck and success.